Hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I welcome you all once again for this 8th interaction session on the course Atomic and Molecular Physics, which is being flowed this January 2026 session with course code NOC 26 PH18. Today we will be discussing a few sample problems which will be covering the course content of week 8 lectures. So if we start discussing about the content that was covered in this week, so if we talk about week 8 lectures, so it is from lecture 36 to lecture 40, and it was uh, mainly about a few lectures was about quantum mechanical treatment of hydrogen atom, which was continued from the last week's discussion. So quantum mechanical treatment of hydrogen atom, then concepts of atoms in a magnetic field, atoms in magnetic field, which is also called as G-man effect. In G-man effect, what happens basically when the atoms are placed in a magnetic field, we know uh, electrons in an atom, when they uh, move around the nucleus, then each orbital, the orbital motion of electron or the spin motion of electron, they give rise to magnetic moments. So depending upon the states in which the electron is moving, we will be having a magnetic dipole moment. So the magnetic moment. So whether it be spin magnetic moment or orbital magnetic moment, that depends upon the motion we are considering. Then that will interact with the external magnetic field. So when the atom is placed in an external magnetic field, so it will be having some interaction energy, and which will again perturb the energy of the atom, basically energy of the electron, and due to which there will be splitting of the spectral lines. So we will be this concept was also discussed, and then towards the end of the week in lecture 40, Stark effect was used, which is basically atoms in electric field, which is also called as Stark effect. So let's first briefly discuss about uh, G-man effect. So if you talk about G-man effect, G-man effect is the splitting of the spectral line in presence of a magnetic field. Splitting of spectral lines in presence of magnetic field. So there are two types of G-man effect. One is called as normal G-man effect, and another is called as anomalous G-man effect. So the normal G-man effect considered normal G-man effect is basically when spin is not considered, so spin equal to 0. So in which a single spectral line that splits into three spectral lines which are equally spaced depending upon the selection rule. One corresponds to delta, since we are not considering S, so only the uh, quantum number which plays significant role is quantum number L, that is orbital magnetic quantum number. So according to the selection rule, delta ml 0 or plus minus 1. So delta ml 0 corresponds to one line, delta ml minus 1 corresponds to one line, and delta ml plus 1 corresponds to one line. So each spectral line gets splitted up to three equally spaced spectral lines. It is called as normal Zeeman effect. And then anomalous Zeeman effect, when the spin is considered. So in that case, one spectral line gets split into more than three on equally spaced spectral lines. So if you talk about normal Zeeman effect, what happens? As we already discussed, there is no spin that is to be considered. So will be mu L vector, that is the magnetic moment coming out of orbital motion of electron, which will be minus GL mu B by H cross L vector, where we know GL is equal to 1. So in that case we can write equal to minus mu B by H cross into L vector. Now this, when it is interacts with the external magnetic field, so the interaction energy will be minus mu vector dot B vector. So it becomes mu B by H cross L vector dot B vector. So due to this interaction, we know L dot B, the magnetic moment along Z direction, Lz we know Lz is MLH cross. So we can write it as mu B divided by H cross into B Lz, or mu B divided by H cross into ML H cross. So H cross gets cancelled out. So delta E is mu B B ml. So depending upon the value of ml, so here ml has significance. So depending upon the value of ml, we will be having different energy levels, and the selection rule will be 0, +1, -1, and we will be having 3 levels. Similarly, if you talk about the splitting of spectral line, it is according to the formula EB by 4 pi m that were discussed in week's lecture. Similarly, if you talk about normal anomalous Zeeman effect, so let's add a few slides. So in anomalous Zeeman effect, so in anomalous Zeeman effect, what happens? We need to consider the spin motion. So due to spin and orbital motion, due to LS coupling, it gives rise to J vector. So L vector plus S vector, they give rise to J vector. That is the total angular momentum vector. So in that case, the magnetic moment is represented by mu J vector is equal to minus Gj mu B by H cross J vector. So here Mj will be having significance, and we need to find the value of Lambda G factor, which is called as Gj, Lambda G factor. So in that case, what happens? So the energy levels, they are arranged in terms of J value. So the label, so like in the previous case, the label was splitted depending upon the ml values. Like if the value is L, so it will be splitted into 2L plus 1 labels in magnetic field presence. So this was in normal Zeeman effect. Then in anomalous Zeeman effect, Mj will be playing an important role. So J, so the label will be split into 2J plus 1 labels. But there is another effect which is called as Bastian wave effect, and that basically occurs in presence of strong magnetic field. So in strong magnetic field, what happens? The orbital and spin motion of electron, they become uncoupled. That is, the coupling between spin and orbital motion, that is break. So here it will be split into. So in case of Bastian-Beck effect, it will so both ML and MS, they have significance. So it will be split into 2L plus 1 into 2L plus 2S plus 1 and 2L plus 1 labels, and so selection will be different. And similarly, this was all related to magnetic field. Now when the atom is present in electric field, then what happens? The perturbation occurs in the total energy. So depending upon the level of perturbation, this is called as Stark effect. And the Stark effect, it can be again linear Stark effect and quadratic linear or quadratic. So these were a few concepts that were discussed. So now let's discuss. So now let's discuss a few sample problems that are based on those concepts. So first we will start with some of the problems related to quantum mechanical treatment, and then we will discuss problems related to G-man effect and Stark effect. So now the first question. So the question says a normalized ground state wave function. So the question says a normalized ground state wave function of a hydrogen atom is given by psi function of r is 1 by root pi a to the power minus 3 by 2 e to the power minus r by a, where a is the smallest Bohr radius and r is the distance of the electron from the nucleus located at the origin. Now we need to find out the expectation value of 1 by r square. The options are option A 2 by a, option B 2 by root a, option C 2 by a square, or option D 1 by a cube. So these are the four options. The question says, so the wave function is given. Wave function is a function of r only, and so which is given by 1 by root pi a to the power minus 3 by 2 e to the power minus r by a, and we need to find out the expectation value. So I'll give you a few minutes and then we will discuss. So let's solve this one. So we know in case of quantum mechanics, all the values are represented in terms of expectation values. So we know there is a formula to calculate the expectation value. So the expectation value of a particular physical quantity, that is 1 by r square, it is written as expectation value or average value. It will be integration psi star psi 1 by r square dr, or more suitably we can write psi star r 1 by r square psi r dr. So now we have the expression psi r, so we will put the expression for psi r here and we will calculate the expectation value. And again, it should be um, kept in mind that the expectation value, the here it is dr, not it is dr, it is dv. So it will be 4 pi r square dr. So dv will be 4 pi r square dr. So 1 by r square expectation value equals to 0 to infinite. So the expression for psi r is 1 by root pi a to the power minus 3 by 2 e to the power r by a. So it will be 1 by root pi a to the power minus 3 by 2 into e to the power minus r by a into 1 by r square into 4 pi r square dr into again psi r 1 by root pi a to the power minus 3 by 2 e to the power minus r by a. So here r square gets cancelled out, 4 pi will be coming outside, then 0 to infinite. So here since there are no imaginary part of the wave function, so both the wave function and the complex conjugate, they are same. So what we get, we will get, so again root pi, it will get cancelled with pi. So we can write 1 by pi e to the power minus 2r by a into a to the power minus 3 into dr. So it will be 4 because pi gets cancelled out, 0 to infinite. So 4 by a cube we can take outside. It will be e to the power minus 2r by a dr, and the integration is quite simple. It is 4 by a cube 0 to infinite e to the power minus 2r by a, sorry, let me wait one second. So 1 by r square will be 4 by a cube e to the power minus 2r by a divided by minus 2 by a 0 to infinite. It will be 4 by a cube into minus a by 2 e to the power minus 2r by a 0 to infinite. So it will be minus 2 by a square e to the power minus infinite minus e to the power 0. So e to the power minus infinite is 0. So it will be minus 2 by a square, 0 minus 1. So it will be 2 by a square. So the correct option is option C, 2 by a square. So the expectation value of the quantity 1 by r square for hydrogen in its ground state, this is the ground state wave function, it will be 2 by a square. I hope this is clear to everyone. Now we will move to question number 2. So the question number 2 says the total number of G-man components observed in an electronic transition of 2d 5 by 2 to 2p 3 by 2 of an atom in a weak field is, options are option A 4, option B 6, option C 10, or option D 12. So here the question related to G-man effect. So we need to, sorry, so we need to consider the concept of G-man effect here, and the transition is occurring from 2d 5 by 2 to 2p 3 by 2. So we know there are two types of G-man effect. One is normal G-man effect, another is anomalous G-man effect. And in case of normal G-man effect, spin is 0, but here as you can see, 2s plus 1, it is 2, so s is half. So spin is not equal to 0, so it is the case of anomalous G-man effect. So that's why we need to use the concept of anomalous Zeeman effect to find out the total number of Zeeman components. So I'll give you a few minutes to think about this question and try to solve it, and then we will discuss briefly what will be the correct answer. So if we solve it, so here it is the case of anomalous Zeeman effect, because here the transition is occurring from 2D 5 by 2 to 2P 3 by 2. So in this case, it is uh, corresponding to spin half. So since spin is not equal to 0, so it is anomalous Zeeman effect, and in the levels it will be getting splitted into uh, different levels depending upon the value of j. So here if you so j value, it will be split into number of mj values. So for j equals to 5 by 2, we have 6 mj values. So starting from plus 5 by 2 to minus 5 by 2. So plus 5 by 2, 3 by 2, half, minus half, minus 3 by 2, minus 5 by 2. Similarly, for j equals to 3 by 2, 4 mj values, it will be 3 by 2, 1 by 2, minus 1 by 2, and minus 3 by 2. So, if we talk about the transitions, so initially it was uh, 2d5 by 2 and 2p3 by 2, but in presence of magnetic field, it will be splitted into a number of levels. Again, it will be splitted into a number of levels. So let's go to the next page. Here we can write it is 2d 5 by 2, and it will be splitted into 6 levels. 1, 2, 3, 4, 5, 6. So depending upon the mj values, minus 5 by 2, minus 3 by 2, minus half, half, 3 by 2, 5 by 2. Then 2p 3 by 2 is splitted into 5 levels, sorry, 4 levels. 1, 2, 3, 4. It is minus 3 by 2, minus half, half, 3 by 2. So now the selection rules are delta mj 0 plus minus 1. Selection rule is delta mj equals to 0 plus minus 1. So in that case, what will be the, so from 5 by 2, transition will occur from 3 by 2. So 5 by 2 to 3 by 2, it will be 1. 3 by 2 to half, it will be 1. Half to minus half, and minus half to minus 3 by 2. So these are 4 transitions. Similarly, another 4 will be from minus 3. So then 3 by 2 to 3 by 2, this is delta mj equals to 1. Similarly, delta mj equal to 0, it will be 3 by 2 to 3 by 2, 1 by 2 to 1 by 2, minus 1 by 2 to minus 1 by 2, minus 3 by 2 to minus 3 by 2. So this is delta mj 0. Similarly, another 4 will be for delta mj minus 1. It will be half to 3 by 2, half to 3 by 2, minus half to half, minus 3 by 2 minus half, minus 5 by 2 minus 3 by 2. It is minus 1. So there are, this is 4, this is 4, this is 4. So total there will be 12 lines. So it will be having 12 components in a weak field. Also, it should be kept in mind that here the in the question it is mentioned as weak field. So in presence of weak field, there will be anomalous Zeeman effect, because we, in case of weak field, the coupling between orbital and spin, that will not be broken. So we need to consider the LS coupling, and we know due to LS coupling, it give rise to total angular momentum, that is J. So and depending upon the value of J, the labels will be splitted. So here the correct option will be option D, that is 12. I hope this is clear to everyone. Now we'll move to question number 3. So question number 3 says a sample of a certain element is placed in a zero point 0.3 Tesla magnetic field and it is suitably excited. How far apart are the G-man components, that is delta lambda, of the 450 nanometer spectral line of this element? So the sample is placed in a magnetic field of zero point 0.3 Tesla. So the magnetic field strength is given, which is zero point 0.3 Tesla, and the G-man, the line which is to be considered to be getting splitted is 450 nanometer. So in presence of magnetic field, that is zero point 0.3 Tesla, what will be the splitted lines? That will be what will be the G-man shift, that is the component delta lambda, that we need to find out. So I'll give you a few minutes and then we will discuss. So now if we solve it. It says a sample of certain element is placed in 0.3 Tesla, and we know the separation of G-man component is given by the separation of G-man component is given by delta nu is EB by 4 pi m. Now we know nu is given by C by lambda, that implies delta nu is equals to minus C by lambda square delta lambda. So C by lambda square delta lambda is EB by 4 pi m, that implies delta lambda will be EB by 4 pi m into lambda square by C. If you put all the values, E is 1.6 into 10 to the power minus 19 into magnetic field is 0.3 Tesla into this is 450 nanometer. So 450 into 10 to the power minus 9 square, converting it into meter. 4 into pi is 3.142 into m is mass of the electron, 9.1 into 10 to the power minus 31 into the speed of light, 3 into 10 to the power 8. So now if we solve it, it will be coming out to be 0.02865 angstrom. So the correct answer is option A, 0.02865 angstrom. I hope this is clear to everyone. Now we move to question number 4. The question number 4 says the wave function of the electron in ground state for one electron atom is given as psi 100 is 1 by root pi z by a0 to the power 3 by 2 into e to the power minus zr by a0, where a0 is the smallest Bohr radius and r is the distance of the electron from the nucleus located at the origin. Now, what will be the expectation value of r, where z is the number of protons in the nucleus? So z is a constant, which is basically the atomic number, that is the number of protons in the nucleus, and the options are option a0 by z, option B a0 by 2z, option C 3a0 by 2z, or option D 2a0 by z. So these are the 4 options, and we need to find out what will be the expectation value of r. And the wave function is given 1 by root pi z by a0 to the power 3 by 2 e to the power minus zr by a0. So I'll give you a few minutes and then we will discuss. So now if we solve it, we know the expectation value of r, it will be 0 to infinite psi star r psi r 4 pi r square dr. So 4 pi will take outside, 0 to infinite 1 by root pi z by a0 to the power 3 by 2 e to the power minus 2 z r by a0 into r square into 1 by root pi z by a0 to the power 3 by 2 e to the power minus 2 zr by a0. So 4, this pi will get cancelled out here. It will be 4, 0 to infinite z by a0 to the power cube into r cube into e to the power minus 2zr by a0, 2zr by a0 into dr. Actually, there is a integration formula which says integration 0 to infinite x to the power m e to the power minus x dx is equals to m factorial. So this is an integration formula that we will use. So x to the power m e to the power x. So here x is 2zr by r0. So 2zr by a0. So what we can write here? So expectation value of r will be, so 2zr by a0 cube. You see here 2zr by a0 means 2zr by q means we multiplied here by 2zr. So here z by a0 was there. So 2r, let me write, then I will explain to you. E to the power minus 2zr by a0 into d 2zr by a0. So here additional 2zr by a0 we considered here. So here we need to write a0 by 4z. How? So initially it was 4 outside. So when we consider 2 cube is 8. So it will be divided by 2 only. Then since 2z by a0 we consider here, so a0 by 2z we need to divide. So it comes out to be a0 by 4z. So now you see this is x to the power m e to the power minus x dx. So which is m factorial. So here m is 3. So we can write it as a0 by 4z into 3 factorial. So the expectation value of r will be a0 by 4z 3 into 2, that is 6. So it will be 3a0 by 2z. So the correct answer is option B 3a0, option C 3a0 by 2z. So the expectation value of R in ground state of hydrogen atom is 3a0 by 2z, and the expectation value of 1 by r square is 2 by r square, that we discussed in the first problem of today's interaction session. I hope this is clear. Now we will move to question number 5. So question number 5 says the probability that x lies between x and x plus dx, that is px, is a e to the power minus ax dx, where x ranges from 0 to infinite and a is a positive constant. Now, what will be the probability that x lies between x1 and x2, where x2 is greater than x1? So basically, it is related to the concept of quantum mechanics, and we know in case of quantum mechanics, the probability. So px, it is given as a e to the power minus ax dx, but we need to find out the probability between x1 and x2. So what will be the probability? So it will be integration of limit x1 to x2 px dx. So we need to find the value of this integral, then that will be the answer. So if you calculate, so p, it will be integration x1 to x2 px dx. So p is a e to the power minus ax into dx. That implies a divided by minus a e to the power minus ax x1 to x2. So p will be minus 1 e to the power minus ax x1 to x2. That implies minus 1 e to the power minus ax2 minus e to the power minus ax1. So it will be e to the power minus ax1 minus e to the power minus ax2. So the correct option is a e to the power minus, sorry, e to the power minus ax1 to e to the power minus ax2. So the correct option is option C. So it was a question related to the generalized concept of quantum mechanics, that is how to find out the probability of finding a particle if the probability function, that is the wave function. Basically, it is uh, we can write it as psi x and the probability of finding the particle between the two positions x1 and x2. Now we move to question number 6. Question number 6 says, find the minimum magnetic field needed for the G-Man effect to be observed in a spectral line of 400 nanometer when a spectrometer whose resolution of 0.010 nanometer is used. Options are option A 1.025 Tesla, option B 1.325 Tesla, option C 2.005 Tesla, or option D 3.55 Tesla. So here the question says, what will be the minimum magnetic field needed for G-Man effect to be observed in a spectral line of 400 nanometer when the spectrometer resolution is 0.010 nanometer. So basically here we need to find out corresponding to a G-Man splitting of 0.010 nanometer, what is the minimum magnetic field required? Because we know under the presence of magnetic field, the spectral line gets split into a number of spectral lines, which is called as G-Man effect. So in order to have a significant amount of splitting, that is delta lambda, we need a particular value of magnetic field. So that minimum magnetic field needed for splitting up 400 nanometer spectra into the shift up or the delta lambda of 0.010 nanometer. So delta lambda is given here as 0.010 nanometer and lambda is given here as 400 nanometer. So what is the magnetic field required? That will be the answer this question. So I'll give you a few minutes and then we will discuss. It is pretty much similar to the question that we had solved earlier, but the only difference is the unknown here is different. In that question it was 0.3 Tesla and we needed to find out the splitting, and here the splitting is given, we need to find out the magnetic field. So the expression will be delta lambda is EB by 4 pi m C by lambda square by C. So B will be C delta lambda into 4 pi m divided by E lambda square. So now what will be B? So B equals to 3 into 10 to the power 8 into the splitting is 0.01 nanometer, 0.01 into 10 to the power minus 9 into 4 into pi is 3.142 into mass 9.1 into 10 to the power minus 31 divided by 1.6 into 10 to the power minus 19 into lambda square is 16 into 10 to the power minus 14. So it is 400 nanometers. So 400 square into 10 to the power minus 18. So we can write it as 4 square into 10 to the power minus 14. So if we calculate it, it will come out to be 13.25 into 10 to the power minus 1 Tesla. So B is 1.325 Tesla. So the correct answer will be option B, 1.325 Tesla. Now I move to question number 7. Question number 7 says a sample of certain element is placed in 1 Tesla magnetic field and it is suitably excited. How far apart the G-man components of 500 nanometer spectral lines of the element will be? Options are option A 0.1178 Armstrong, option B 0.058 Armstrong, option C 1.002 Armstrong, or option D 1.235 Armstrong. So again this is pretty much similar to the question we solved just now. So what will be the correct answer? So again we will use the same formula. Delta lambda is EB by 4 pi m into C by lambda square. Sorry, I think we need to change it. It will be lambda square by C. So 1.6 into 10 to the power minus 19 into 1 Tesla into 25 into 10 to the power minus 14 divided by 4 into 1.132 into mass is 9 into 10 to the power minus 31 into C is 3 into 10 to the power 8. So if we calculate it, it will come out to be 0.1178 Armstrong. So the correct option will be option A, 0.1178 Armstrong. Now we move to question number 8. Question number 8 says, calculate the internal magnetic field produced by the nucleus which causes the splitting of the 3p state of the sodium atom, given the energy of the sodium D1 and D2 lines are 2.1093 electron volt and 2.1 2.1071 electron volt respectively. So let's understand the question first. The question says calculate the internal magnetic field produced by the nucleus which causes the splitting of 3p state of the sodium atom given D1 and D2 lines are of energy this volt and this volt. So here we need to find out what was the magnetic field that was produced by the nucleus due to which a single level, that is 3p state, that gets splitted into D1 and D2. So the energy of the D1 and D2 lines are 2.1093 electron volt and 2.1079 electron volt. So here we need to find out what is the so what is the magnetic field that was produced due to which the splitting between the two levels occurred and the levels were separated by this energy. So the difference in energy will be 2.1093 minus 2.1071, and that splitting is due to the interaction between the magnetic moment and the magnetic field. So here we need to find out what will be the value of the magnetic field that led to the splitting of the 3p level. So these are the options. Option A 15.5 Tesla, option B 3.25 Tesla, option C 18.97 Tesla, or option D 7.5 Tesla. So this is an important question that we will discuss briefly in a few minutes. But before that, I'll give you a few minutes so that you can try and solve this. So now what is the difference in the energy? So D1 it is 2.1093 V and D2 is 2.1071 eV. Now this D1 and D2 line that come into picture due to the consideration of magnetic sorry, electron spin. So one is spin up, another is spin down. So what will be the energy difference? So the energy difference delta E will be 2.1093 minus 2.1071. So it will be 0.0022 EB, that is 2.2 into 10 to the power minus 3 EB. Now um, what leads to this energy difference? That is the difference is due to separation of spin up and spin down state. So this delta E arises due to separation of spin up and spin down. And we know what is the separation? The separation is 2 mu b into b. So how the separation is coming? One is mu b into b, another is minus mu b into b. So it will be mu b into b minus mu b into b. So 2 mu b b, because we know. So for one case it is spin half, spin minus half, or it is spin minus half, it is spin half. So the energy is this. So the energy difference due to consideration of the electron spin. Now this 2 mu b b, that is equals to 2.2 into 10 to the power minus 3 eV, where what is mu b? Mu b is Bohr magneton, and the value is 9.274 into 10 to the power minus 24 joule per Tesla. So what will be the value of B? So 2 mu b b, it is 2.2 into 10 to the power minus 3 into, in terms of joule, it will be 1.6 into 10 to the power minus 19. Now it will be B. B will be 2.2 into 10 to the power minus 3 into 1.6 into 10 to the power minus 19 divided by 2 into 9.274 into 10 to the power minus 24 joule per Tesla. So it is coming out to be 18.97 Tesla. So it is joule and joule per Tesla. So joule gets cancelled out and only Tesla remains. So the magnetic field is 18.97 Tesla. So the correct option is option C. So due to this internal magnetic field produced by the nucleus, that is the 18.97 Tesla. When this 18.97 Tesla and the spin of the electron is considered, then due to the spin up and spin down motion of the electron, the 3p level gets split into 3p up and 3p 3 by 2, due to which D1 and D2 lines occur, and the energy difference is 22 2.2 millielectron volt. I hope this is clear to everyone. Now we'll move to question number 9. Question number 9 says, find the normal Gaussian energy shift delta E in EV for a magnetic field of 0.05 Tesla. So here you see, here the case is for normal Gaussian effect. So in case of normal Gaussian effect, the magnetic field is present and we need to find out the energy shift for this magnetic field. So we know the change in frequency, that is delta nu, is given by EB by 4 pi m. That implies energy shift delta E, it will be given by H into delta nu. So it will be EBH by 4 pi m. So the options are given: 2.9 into 10 to the power minus 6 electron volt. Option B 2.2 into 10 to the power minus 5 electron volt. Option C 1.4 into 10 to the power minus 7 electron volt. And option D 5.3 into 10 to the power minus 7 electron volt. So if we put the values, it will be E is 1.6 into 10 to the power minus 19 into B is 0.05 Tesla and H is 6.62 into 10 to the power minus 34. 6.626 into 10 to the power minus 34 into 0.05 divided by 4 into 3.142 into 9 into 10 to the power minus 31. So if we calculate, it will be 0.05 into 6.626 into 10 to the power minus 34 divided by 4 into 3.142 into 9.1 into 10 to the power minus 31 electron volt. So it was in joule. So we converted into electron volt. So it will be 6.626 into 0.05 divided by 4 into 3.142 into 9.1 into 10 to the power minus 3. That implies 0.0029 into 10 to the power minus 3 electron volt, or 2.9 into 10 to the power minus 6 electron volt. So the correct answer is option A, that is 2.9 into 10 to the power minus 6 electron volt. Now we move to question number 10. So question number 10 says the fine structure splitting of the level 2p3 by 2 and 2p half level in hydrogen is 4.5 into 10 to the power minus 5 electron volt. For this, estimate the magnetic field that the 2p electron in hydrogen experiences, where we can assume that the magnetic field B is parallel to Z axis. So options are option A 0.53 Tesla, option B 0.028 Tesla, option C 1.09 Tesla, or option D 0.388 Tesla. So the 2p level, it gets split into 2p half and 2p 3 by 2. And in case of hydrogen, the splitting between the level, or the energy difference between the level, is 4.5 into 10 to the power minus 5 eV. The question is solved before, that was related to sodium. So sodium has D1 and D2 line that corresponds to the level 2p half and 2p 3 by 2. But it is hydrogen, so it is 4.5 10 to the power minus 5 eV. So from this estimate, we need to find out what will be the magnetic field that lead to this type of splitting. So the options are option A 0.53 Tesla, option B 0.028 Tesla, option C 1.09 Tesla, or option D 0.388 Tesla. So I'll give you a few minutes and then we will discuss what will be the magnetic field that will give rise to the splitting of 4.5 into 10 to the minus 5 electron volt. So now if we solve, we know the interaction energy is given by minus mu vector dot p vector. So similar to the spin, depending upon the spin, the interaction energy was 2 mu bb. So 2 mu b was 4.5 into 10 to the power minus 5 pb. So what will the magnetic field? So B will be 4.5 into 10 to the power minus 5 into 1.6 into 10 to the power minus 19 divided by 2 into 9.274 into 10 to the power minus 24 and 4.5 into 1.6 divided by 2 into 9.274 into 10 to the power minus 24 plus 24. So B will be 0.388 Tesla. The correct option is option D, that is 0.388 Tesla. So we know, so the splitting, like we had already discussed here, the splitting was due to the spin of spin down motion, which is 2 mu bb. So due to the magnetic field effect, it got splitted into 2p3 by 2 and 2p half, and that led to the energy difference of 4.5 10 to the minus 5 pb. So if you calculate, the magnetic field will be 0.38 Tesla, because the interaction energy is 2 mu bb, where mu b is Bohr magnetron. So with this, we come to the end of today's interaction session. I hope the questions that I have solved today will definitely help you in preparing your exams, for preparing for your exam preparation, as well as for solving the assignment questions that you are facing this year course. With this, I end this interaction session. Again, thank you all for joining.